complex numbers. So a complex number basically has two parts to it, the real part and the imaginary. So a complex number is a fusion of everything we've learned so far. So the real numbers and the imaginary numbers that we're learning right now. So a complex number is a set of all numbers of the form a plus bi. So the big takeaway here that I need from you is that really is in two parts. Two parts. You have the real plus the imaginary. So in the homework for a complex number, you have to split things up. So if you get like 3 plus 2i over 7, in the homework system, you have to put this in as 3/7 plus 2/7 I. Okay, it has to be, that looks like mischievous there. That's better. So you have to have the two parts separate. It has to be crystal clear what's real, what's imaginary. So if we only have just the first part, it's a real number. If you only have the second part, that's the imaginary that we've talked about already. So these numbers can be added, subtracted, and multiplied and divided. The first three operations are very similar to what you've known your whole life, or your mathematical career, I should say, in that you're just combining like terms. So 2 plus 3i plus negative 3 plus 5i, all that is you combine the 2 and the negative 3, that's negative 1. And then you combine the I parts. So 3i plus 5i, that's 8i. That's it. Bingo, bango. Here, you're just distributing the negative. So you've got 4 minus 2i minus 3 plus 7i. And now, just like above, you're combining like terms. So 4 minus 3 is 1. Negative 2i plus 7i is what? Plus 5i. And that's it. Here, for these next two, you are treating them just like binomials, as if the I was an X. So distribute, so 2 times 4 is 8. Distribute, 2 times 3i is plus 6i. Distribute, that's plus 20i. Distribute, that's what? This is actually plus 15i squared. This is what will get most people, so be careful here. Because it's I times I, which is I squared, but what's I squared? Negative 1, right? So that's not plus 15. This is negative 1, which in turns make this a subtraction sign. So to simplify this, it's 8 minus 15, which is negative 7. And then plus 6i plus 20i is plus 26i. So let's try another one. 3 times 3 is 9. 3 times 2i is plus 6i. Negative 2i times 3 is negative 6i. Negative 2i plus 2, or times 2i is minus 4i squared. But what does this become? That really becomes plus 4. These are reducing to 0. So this is really, remember, 9 plus 4, which is equal to 13. Hopefully that wasn't too bad. So now, top of the next page is actually the generic version of what we just talked about. It's a specific pattern, and these two things are called conjugates. Okay, these two things are called conjugates. Conjugates are when you have a binomial. Bi means 2, right? A binomial, almost a carbon copy, except your operations are opposite. Positive one, negative the other. Excuse me, I should say addition and subtraction. So conjugates are really nice because something happens every time that you just looked at above, is that the middle two terms zero out every single time. Every single time. So here, pardon me, a times a is a squared. A times negative bi is negative abi. Bi times a is plus abi. And now bi times negative bi is minus b squared I squared. So notice here, like I said, these two terms cancel out every single time. Remember, I squared is -1, so it's going to make this positive, right? Because I squared is -1. So realistically, all we have here is that you end up with a squared plus b squared, which is what we got here, because what's 3 squared? 9. What's 2 squared? 4. So the summation of a squared plus b squared is 13. Pretty cool, right? So why you have to know that, why I taught you that, why it's on here, is for division. Because division of conjugates is, it's annoying, okay? Let's not mince words here. It's annoying, it's frustrating. You don't actually ever divide conjugates. Or excuse me, you don't actually divide, complex numbers. What you do is really just get rid of the I from the denominator. And the easiest way to do that is by using conjugates. So if I have 3 minus 5i, remember it's a carbon copy, but you just change the operation. And we're using that special version of 1, because what's anything over itself? 1. What's 1 times anything? The thing you started with, right? So here, what we have is that we're not adding any weight or value to the problem. We're just getting it to look visually different. We're just manipulating it so that it looks a little bit different. So from the pattern above, I know that the denominator is really just 3 squared, which is 9, plus 5 squared, which is 25. Now in the numerator, you really are just distributing. So 2 times 3 is 6. 2 times -5i is -10i. 4 times 3 is plus 12i. And then 4i times -5i is -20i squared. But remember, the I squared is really a -1, so that makes it a plus 20. So now in simplifying, I get 20 plus 6, which is 26. -10i plus 12i is just plus 2i, over 9 plus 25, which is what, 34? But remember what I said a page ago? Complex numbers are in 2 parts, so you don't leave it like this for the same denominators. Like the few times I'll ever tell you to separate denominators. But it's what you do. So here we get 26 over 34 plus 2i over 34, which reduced is what? 26 divided by 2 is 13. Oh, duh, hello. 13 over 17 plus 1 over 17i. Let me just double check that real quick. Don't ever trust anything I do in my head. That would be a silly mistake. Perfect. All right, and that's it. Well, that's it for this video. Not done with complex numbers.